but that's not a problem, right? That's good.
Yeah.
It's not everything people like to think. You got to give them a chance to try things, but it should be an option to try. It shouldn't be a predetermined decision. You know.
All right, let's get started. Got quite a few people online. We've got a good group here in person. And as always, we'll start with a few announcements before we turn it over. So I think the big one is that the legislature, the Ag Conference Committee finished their work. They passed the bill. I don't know if it's been passed on the floor and signed, but essentially the deal is done. Has it been signed? Or
No, the governor, well, it'll take the governor time to sign.
yeah. His hand starts to cramp up, so gotta deal with that. But the upshot is Forever Green Research, the Forever Green Initiative, is receiving $802,000 a year. I don't know where the two came at the end, but 802 a year, this year, next year, and with tails into the future. So that is the really, really exciting part of it, that can stabilize. We can use those funds to stabilize key people and functions of Forever Green in a way that previously they've all been dependent on soft money or unstable funding. So hooray, thank you to our advocates who worked so hard at the legislature to get that done. Huge victory, huge advance for Forever Green. At the same time, in the same bill, there's another $500,000 allocated to the value chain, the CLC value chain grants. And I'm just starting to hear news trickling in of who received the first round of those grants, which I don't think, I'm not totally comfortable sharing that in this wide of a group yet, but the first round of grants apparently have been announced to the winners and those who did not receive them. So we'll probably be learning more soon. These are designed to go to supply chain businesses, essentially. We're building the supply chain for our crops and other related crops. And so there'll be another $500,000 in this next 2-year period to allocate to that grant program. So also very exciting and good support. It also looks pretty much done deal on the Clean Water Council funds, $6 million. Those are passed on both sides. It's identical, bills are identical, so that should sail through. So altogether, a very successful session for Forever Green. Do you want to add anything on that, Don? Or
No, I would just say that we have a big field day coming up on Monday. The Clean Water Council, the ones that supported that $6 million investment in us, are coming for a tour on Monday. A number of you are aware of the schedule for Monday, so it's going to be, I hope, a very nice day. Weather forecast looks good. So we'll be meeting here. We'll take them out for the tour, and then Beth Dooley will be serving a Forever Green crop-based lunch with beer from Bang Brewery. So that will be, I think, another great day for all of us.
So maybe joking.
Exactly. And I also want to introduce to you one of the alumni of the Forever Green Initiative coming to us today, all the way from Hawaii. Dr. Mikey Kantar was one of the former PhD students in the program that led the development of the perennial sunflower and played a key role in work on the perennial flax. And also captain of the University of Minnesota tennis team as an undergraduate.
yeah, any other announcements for the good of the cause here before we turn it over? Anyone online? Carmen, speak up.
Yeah, we just discussed this morning about our big field day coming up July 13th here at the farm, and we're going to have some filming crew out here working on a documentary with Wes Jackson. So stay tuned for more details as they fall together. July 13th, a Thursday.
So if you want to be famous, go to Carmen's Field Day this year and you'll get in the movie. Is that the story?
Yeah, right. We expect you to be there, Mitch.
Oh, I'm planning on it.
Good.
Anyone else have announcements? All right, let's turn it over to Walid and his team. Please introduce yourselves and take us away.
Cool. All right, so thanks everyone for being here today, both in person and online. I've been asked to be involved in this research project. Turns a team to work on a question that is important, which is trying to understand the basis of this interannual yield decline that has been observed. And so this team has been set up to address this question. So I'm highlighting here two people who will be presenting their research: Xiaoxing Zhen, who's a postdoc, and Qiansu Ding, who's a PhD student. Obviously, Jake Jungers is involved, and he contributed a lot in terms of providing data for the first objective of this presentation, which I will illustrate. Prabin and Jim Anderson providing the genetic material to investigate some questions. Daniel, who was instrumental in conducting those field-based measurements as well, and Catherine Bourne in terms of providing help for the yield analysis in the field experience. So this is a kind of multidisciplinary core team. So I'm the speaker here, Walid. I'm a crop physiologist, agronomy engineer, and I'm interested in understanding how plants respond to crops respond to the environment and how to improve their productivity and ability to provide ecosystem services. So this is the outline of the presentation today. I hope we'll leave enough room for discussions and exchanges. I will just take the floor for a few minutes to provide the background and the project rationale. Then Xiaoxing will take it from here to address the first part, which is trying to understand the kind of parse out, characterize that yield decline, and then move on to Qiansu, whose PhD thesis and work focuses on understanding the physiological basis. So I don't think I do need to dwell too much on the challenge in front of us, and there are a couple of papers recently published addressing this, which is the widespread adoption of intermediate wheatgrass hinges on the yield performance, especially as the crop moves from throughout the years, because this isn't intended to be a perennial crop. And there is evidence, and this is something I noticed when I joined the discussion, that there is yield decline in Minnesota, but there is no clear, characterization when it comes to the magnitude and the consistency. And here there's a slide prepared by the former postdoc who worked on this, who started actually this effort I'm going to outline, who's Michelle Dobratz, who did a really nice job. But as part of her introduction is to show a slide like this to show that there are, depending on the location and maybe the treatment, you have a decline starting from year 2 or from year 1, etc. So this raises the question for us to build a yield database. This database compiles a large number of experiments published, and Xiaoxing will detail the analysis of this database. And this is spearheaded by Jake. So we have a large number of parameters here on experiments representing 24 location years, covering 2012 to 2019, thousands of entries representing 25 experiments, and 123 unique descriptors of agronomic variables, soil data, weather variables, etc. So I'm not going to dwell too much on this so that I don't steal the shine from Xiaoxing.
Last year we talked about this in terms of where the data set came from. Is all the data from Minnesota, or does it now include other sites?
So the data is from Minnesota, but because that's the question we wanted to address in the renewal, which was not funded. So the question that I asked by Xiaoxing is, what is the extent and magnitude for the progressive yield decline in intermediate wheatgrass in the Minnesota conditions? And what you try to come up with is, what is the typical timing of this? What is the relevant, what is the level and pattern of this decline? And this is actually the most important question, which is to understand the relative contributions of the environment, both in terms of management practices and also in terms of climate and cultivar choice. And you will see that there are some interesting findings there. So that's part one of the presentation. And then there is the second part, which is about the physiological basis of what's going on. And the key idea here is that we have to remember that intermediate wheatgrass is still being domesticated, as shown in this figure here that shows yield gains as a function of the breeding cycle. So breeders are doing something to increase the yield here. So the yield potential is increasing. But this observation of interannual yield decline clearly suggests that there are some agronomically unfavorable, but what we presume are evolutionarily favorable traits that are still harbored by the crop. I mean, one of those key traits, simple traits, would be shattering, right? That has to be bred out from crops during domestication. But in the case of perennial grains, the challenge is basically the trade-off between reproduction and longevity, and which is framed in the theory, in ecological theory, called theory in chains of optimal evolutionary strategy, which is basically this characteristics that perennial grains do. They shift from year one to year two and the following years between a competitive strategy to a tolerant strategy. I'm going to explain this in a couple of slides, and then I will stop my part, because I think this is an important framework to outline. So the idea is reasonably straightforward. So young plants basically incur high mortality risk. They grow from seeds, and their goal is to grow fast and to photosynthesize more aggressively and perform high levels of gas exchange. And their priority, they need to achieve a higher seed-to-seed cycle. They need to produce more seeds to survive. The question for older plants, year two onwards plants, they incur lower mortality risk, but they have a lot of maintenance costs. They have to sacrifice photosynthesis. They perform conservative gas exchange, and they do that. Invest carbon and nitrogen in metabolically costly maintenance and stress tolerance costs. They have rhizomes. They have extensive root system that respire, that have to tolerate and adapt to shifting population of microbes in the soil. So it's a big individual when it's old. However, the incentive, evolutionarily speaking, for younger plants is to invest that carbon and nitrogen in the seeds. So that's the space, the trade-off space. So, but we need to confirm that. And the hypothesis here addressed by Qiansu, which were framed by her, examined by her. So the decline in gas exchange is driving the interannual yield decline at least between year one and year two. Particularly photosynthesis rates, and or a decline in photoassimilate and nitrogen remobilation through the seeds, and or a decline in ability for stress tolerance as the plant progresses through those years. Okay, so these are the two key frameworks: the database analysis by Xiaoxing to understand what exactly the problem that we're dealing with, and then Qiansu will take it from there to kind of give us some input, some recent results about it. So what we think is going on.
Okay. Yeah. Hello, everyone. I'm Xiaoxing Zhen. This is my second year working with grass. For my research, I would like to see if yield decline happens in Minnesota, in which year the yield decline happens, and are there any management practices or environmental factors can reverse or can reduce the yield decline. And as introduced by Walid, we collect a large database with Jake's team. This is a summary of the data. It has 8 sites distributed in Minnesota. There are different soil types, different temperature and rainfall, and the earliest year from year 2012. The latest year was from the year 2009. Most of the experiments, they have 3-4 years production years. Then we can track how the yield changed in the 4 years. There's many management practices. We would like to see if some management practice can maintain the yield across the 4 years and reduce the yield decline. And then I put all the data together to see if yield decline happens in Minnesota. Yes, it happens. You can see from year 1 until year 4, the yield continue decline. And the biggest yield decline happens in year 1, year 2, and the slope of yield decline is about 200. And then also what's interesting with the harvest index of above ground biomass. According to our data, the above ground biomass for the 4 years do not change a lot. And this leads to the harvest index for the 4 years continue decline. And the slope or yield, the slope or harvest index decline is about 0.02. Then I want to see whether my large database really reflect the yield decline. And we separated the database, and we want to contract the plots which are measured continuously for 4 years. I call them 4 years plots. For this plots, I do a similar analysis compared to the large database. I see the similar yield decline in the 4-year plots compared to all the plots. You can see their slope of yield decline is similar for the all plots. The slope of yield decline is about 0.02. For the 4 years plots, those plots are measured continuous. For 4 years, the slope of yield decline is about 224. And then look at the harvest index in the all plots and the 4 years observed plots. They have exactly the same of harvest index decline for the 4 years. They all the value of 0.02. It shows our large database is a good quality. We can continue based on this large database to many interesting analysis. And okay.
Shouldn't your all plots in year 4 have the same span as your 4-year plots?
Not exactly, because for plot have year 4 data, it's not exactly have year 1 or year 2.
Sure, but if it's in year 4, it implies that it was a 4-year experiment, right?
Yeah.
So that column should have the same numbers. shouldn't it?
Sometimes there's some data missing. I don't know what happens, but yeah, there's some plots that do not have the year 2 or year 3 data. I just remove that.
Yeah. I get
data
it for
quality.
everything. I get it for everything except the year 4.
Yeah,
So you're talking about the kind of much lower number of observations the 4th year on panels A and C, is that correct?
Just the fact, not that it's higher or lower, just the fact that it's different.
What
like
the number of observations, right?
D,
Year-
yeah,
year
D,
four.
to me, D should be the same. Because if you have a year 4 of data, it should be a 4-year experiment, right?
Yeah, that's clearly a problem of data missing in the database, you're right.
yeah.
I mean,
that-
I think, Jake, I don't know if Jake is the audience, because he knows the data,
Okay.
his data, but.
Yeah, we
Fair enough.
double check those database to make sure we do not make error. I check it again. Yeah.
So the other thing is that, and correct me if I'm wrong, because you know the database more than anyone.
Yeah.
In some cases, the data starts from year 2 to year 3, year 1. And for the panel D and B's, it's experiments where 4 years are included. So it's basically the same plot measured from year 1, year 2, year 3, year 4. In the left-hand side of panels, you have experiments where the data that is available to us says year 2 yield, and then year 3 yield, year 4 yield. And therefore, those kind of observations don't make it to the ones. So it's a very conservative data set, the one that you see on the B and D panel. It's like 75 plots where for sure we have yields continuously measured over 4 years. Now, imagine if those slopes were completely different compared to the on the right-hand side compared to the left-hand side. That would be a problem for us, which means that the entire data set is not representative of this very conservative experiment. And that discrepancy would throw us in the direction where we try to fix it, etc. Or understand what's going on.
Yes, we observed the yield decline in the large database. And then the second question is, are there some main practice and also environmental factors can reverse the yield decline? The first main practice we are interested in is nitrogen rate. You can see we have the low nitrogen and the middle level nitrogen and high nitrogen. The year one, there's 1, 2, 3, 4, stand for year one until year 4. From here, we can see even you have a very high nitrogen rate applied, there's still yield decline for the 4 years, according to our database. And the use of nitrogen, optimize the nitrogen rate use do not improve the yield decline, but it actually improve the average yield for the 4 years. You can see for the medium nitrogen and the high nitrogen, you have a higher yield compared to the low nitrogen. So we still suggest the farmer to use middle nitrogen to increase the yield for 4 years. Then look at the Harvey index for the Harvey index that's affected by the nitrogen use, and the Harvey index do not improve the yield. The Harvey index decline do not improve by use of nitrogen, and there's still Harvey index decline across 4 years. And we found when you have a higher nitrogen use, the average Harvey index across 4 years will decrease. It means when you have more nitrogen use, maybe it have more above ground biomass, have more stem, have more leaves. That do not mean we have more yield for the 4 years, average for 4 years. The second main that is we are interested in the row space. We adjust the row space from narrow, middle, or wider space. So that adjust the row space can change the yield decline. No, do not change the yield decline for the 4 years, but it actually improves the average yield for the 4 years. You can see for the narrow space, the space between 10 or 30, it have a higher average yield compared to the middle row space or higher wider row space. And we suggest farmers to use a narrow row space to gain more yields for the 4 years. Then look at the Harvey index. Harvey index continue decline for the narrow space and middle space. There's some change in the wider space, but Harvey index still decline overall for the 4 years. And we can see the highest Harvey index was the average high Harvey index was observed in the wider row spacing. The second main practice we are interested in the seeding rate, change the plant density for the farmers. You can see even we change the plant density from low density to high density, adjust them, there's still yield decline. The yield decline still exists, but if farmers choose a higher density, they may lose their yield. But if farmers choose the middle level or low level seeding rate, they can have an average higher yield across 4 years. And then it's the Harvey index. Does the change in seeding rate affect the Harvey index for the 4 years? Does that reverse the Harvey index decline? They are not reverse the Harvey index across 4 years, but when you in the lower seeding rate, the Harvey index is the highest.
There's a question in the chat.
Yeah.
A couple of questions.
Okay.
So first one from Kevin Smith. Can you separate the year effect from the age effect? 2021 and 2022 were very droughty years compared to earlier years.
Separate the year effect from the age effect. Yeah, that's a nice suggestion. No, I do not consider the drought year and the drought year or the wet year, but for the further analysis, it will be interesting to consider year by year. Does it yield decline was because of drought year or wet year? It's because of stand age. Yeah, that will be interesting.
Yeah.
So I can add a couple of things to that. The database stops at 2019. That's for one. And actually, the rest of the talk, the second part, he examined also some potential association with environmental conditions, which is, so I'll let you talk about. those questions that could be revisited there, but these are important questions. What's the effect of the environment in this?
Yeah.
So.
And there's a second question from Prabin. I'll let you read that. Yeah.
But maybe we could wait for this part to be finished, because he would address the genetics as well. I mean, for the sake of the conversation.
Sounds
Because we
good.
will talk about the genetics, and maybe we can stop after you talk. And then we go back to Jerry, the question, because I think they're important.
Yeah, I can answer all the questions after we finish our talk.
No, you're fine.
Oh, okay. Yeah, I will finish my part.
Right.
Yeah. Thank you for so many questions. Yeah, the last thing we consider is the cultivar, the breeding efforts. If we use the modern cultivar instead of the old cultivar, when they breed the new cultivars for the future, does that reverse the yield decline? The cycle 4 and cycle 2 are the newer cultivars compared to the old cultivars. You can see even for the modern cultivar, cycle 4 and cycle 2, they still have yield decline. It still happens for the new cultivars, but compared to the average yield for the 4 years, then when you breed the new cultivars, the average yield improved. The biggest, the highest yield was the cycle 2. It ranked the highest average yield compared to Roche and cycle 4 cultivars. And compared to the Roche, the cycle 2 cultivar was about 108% higher yield than the Roche cultivars, than the old cultivars. And then look at harvest index. Does the new cultivar have a higher harvest index than the old cultivar? Does the new cultivar reverse the decline harvest index? No, the harvest index decline still exists for the modern cultivars. But it seems that even the cycle 4 have a lower yield compared to cycle 2, but the cycle 4 have a higher harvest index than cycle 2. When you maybe from generation to generation, they have a higher harvest index. And I think the cycle 4 still try to adapt to the environment in Minnesota. I think with the year pass by, maybe cycle 4 have a higher yield than cycle 2. Let's see what happens. And I put all the manipulations and analyze, put them together. We have more analyzed. We do not show today. We have the deforestation analyzed, intercropping analyzed, growth chamber, growth regulator analyzed. And we put them together to see overall what's the overall effect of manipulatics. And let's see does that manipulatics reduce yield decline, reduce harvest index decline? The answer is no. They do not actually reduce the yield decline or reduce the harvest index decline. But when we look at the average yield or total accumulated yield for the overall 4 years, actually, when you try to improve this manipulatics, they improve your accumulated yield for 4 years or your average yield for 4 years. So we still suggest the farmers try to use the best manipulatics to gain more benefits, yield benefits for the overall 4 years. Okay, after I analyze the manipulatics, I tried thinking about whether there's some maybe environmental factors can reverse the yield decline, can improve the yield for the 4 years. And this kind of like QDS analyze we use. Look at the age size, the yield decline has. Oh, okay. Okay. Yeah. Look at the age size we have in Minnesota. The yield decline happens everywhere in Minnesota in the age size. Some sites they have a rapid yield decline. Some sites maybe they have a stable, slow yield decline. And then when we compare the yields, the average yields for 4 years in the age size, the yield pattern in the Minnesota, we found the green one. The higher yield was in the northern and the eastern part of Minnesota. The lower average yield for 4 years was in the western part of Minnesota. And what we're thinking why in some part of Minnesota have a lower yield, some part of Minnesota have a higher yield. We analyze some environmental factors it have. The first environmental factor, we analyze temperature. And the temperature, the higher temperature was in the southern, the lower temperature was in the northern. It seems that the increase of temperature from northern to the southern do not match the pattern of our yield. And then we look at the second environmental factor we have, the rainfall. Does the rainfall pattern match with the yield pattern from the western to the eastern? No, the rainfall increased from the northern part to the southern part, but the yield was increased from the western part to the eastern part. So they are not matched. The yield pattern in Minnesota and the rainfall pattern in Minnesota, they are not matched. There's another factor we consider, it's the VPD. Does the yield pattern distribution in Minnesota match the VPD distribution in Minnesota? Yes, you can see they match perfect. You can see from the western to the eastern, there's a pattern of VPD increase or VPD decrease. And this increase or decrease match well with our yield pattern. And we found that the highest, the lowest yield, highest lowest yield observed in the area with the lowest or highest VPD in Minnesota. And we suppose and we think maybe the high VPD in Minnesota, they change the photosynthesis rate, they reduce the stomachal conductance when the VPD is higher, and they lower the gas exchange, and they finally they lead to a lower yield. That's kind of physiological thinking. Okay, here is my conclusion for my part. I analyzed the managed practice. I observed the yield decline, and I also analyzed the environmental factors in Minnesota. And the first conclusion is the yield decline. Yes, there's yield decline in Minnesota. It had decline about 200 kilograms per helicopter per year. And when we play with the managed practice and cultivars, they do not actually reverse the yield decline, reduce the yield decline. And also we analyzed the biomass and harvest index for the 4 years. It seems that the higher harvest index are not exactly associated with the higher yield. Maybe there's some more information we need to analyze. Then my other conclusion would be that even the breeding of managed practice do not reverse this yield decline, but they still improve the average yield or accumulated yield for the 4 years. It's still worth for the farmers to choose the best managed practice. And for the environmental factors, we actually observe the VPD affect the yield pattern in Minnesota. So it's worth to do more work to analyze why we have a higher VPD, we have a lower yield, we have a lower VPD, we have a higher yield. Yeah, that's maybe my next work to do in the greenhouse and grow chamber in control environment. Okay, I will give my stage. Yeah, maybe answer the question first.
Yeah, I have a question after it's also.
Okay.
Yeah, why don't we take for beans and dairies and then we'll
Okay.
go around.
How did you account for difference in genotype breed? Close or not share or combine?
For bean, it might be helpful if you restate your question out loud to the group, and I think.
Yeah, I worked with Prabin this year to do more analyze. Yeah.
Are you on for bean? Can you ask your question out loud? Okay. It sounds like you two are in touch and you can follow up on that.
Okay.
Oh, my mic isn't working. I'll rephrase it a bit. Okay, so we'll get Prabin a little later. Jerry's question.
Yield is not very useful physiological measurement. Do you have few bigger grains or small grains? Are you mean the kernel number?
Yeah.
The data of kernel number? And from the large database, we have the good quality of yield observation and the biomass observation, but we do not have good maybe kernel number, kernel size observations. That's maybe more detailed data we need to go further. Yeah.
And I would say from my research, I saw that, we did have fewer grains, but that's probably partly because we had smaller grains. It's like compounding because the very smallest, least developed grains get winnowed out effectively and don't really get counted or treated as a grain in the yield calculation, as they shouldn't. They're not really economic yield. So yeah, I don't know if I haven't gone deep enough my own. I think some of Jay's studies have to know if there are really fewer grains on the spike versus fewer grains that reach, a useful size.
I think
It's
to
also
just
good.
to address this question, and because it's important, I think it would be good if in the database we can explore this question of this is something you could work with Jake. I think this is something we're not necessarily delve into. I think that's the right answer about the yield component.
Yeah.
But to answer Jerry's point, I think yield is not a physiological trait for sure. It's not how we see it. Actually, the results from Qiansu experiment might provide some additional insight on what's going on in terms of yield component trait. And I would say the challenge that we grappled with, and Michelle, by the way, she needs acknowledgement here, because she did the parsing, like it's a huge data set, missing data, it's the whole gamut, and extract. This is why we won't work on the 4-year, just to make sure that we're not having structural issues that warp the data in a way that makes us see things that are not there, and vice versa. So the data set, despite it's like the number of location years, is still not deep enough, in my opinion, and especially when it comes to the environmental association aspect. We have correlations, but I will never publish them because they are just based on data that are here and here, and just like you won't bet anything there. So, so there's a challenge there about.
Yeah.
So, Walid, my question wasn't a casual question. If you're trying to measure a physiological trait over time, and you don't know the difference between small seed size and seed number, then you don't know what's regulating the change over the years. You need to know whether your target is seed size or seed number. If it's both, that just makes it more complicated. But it's one of the problems with breeding for first-year yield is you actually may be accelerating the problem by having first-year yield might be kind of like you see in fruit trees with alternate bearing. That first-year yield actually may decline overall 4-year yield. And in order to define that whole physiological process, you need to actually know the physiological trait that you're looking at. So I just put that out there because yield is useless in this case in terms of defining the problem.
As usual, we agree, but just the phrasing is like maybe where we want to agree. So the first part is just about analyzing the database. So we're not seeing yield as a physiological trait per se. And I completely agree with you. And actually the data strongly agrees with you, is that if you breed for higher yields in the first year, the bigger the decline. That's inescapable. So your intuition based on what you're seeing in fruit trees, which I already noticed when I was working on trees, that's completely correct. I completely concur as well with the fact that you need to kind of break down what's going on in terms of yield component traits and connect that to the physiology to understand what's going on, which is not necessarily the goal of the first part, because we don't have that depth of data physiologically to examine those questions. And this is what actually is a perfect segue for chance to speak, but. oh,
Yeah, can I have,
sure,
yeah,
sure.
and I need to get to another meeting, so I just want us to do, yeah, I have a couple of thoughts that I think play off of Prabin's questions also. Yeah, kind of getting at the genotypes and the variability, like I'm curious if you thought about different like meta-analytic methods, like sensitivity analysis because each of the, you have a lot of studies that within each study have a lot of different measurements and those can't be considered independent because it's within one study. And so like, in the world of meta-analyses, there are lots and lots of methods that you can get at that, like, do we have, like, what is this robustness of this one study? If this one study was taken out, would it throw things off? Would it, there's a lot you can dig into with this data set to get at, it's the independence, which could get at like the question Prabin had about the genotypic variation also, like I think it'll be super important in this study to at least publish in the supplements, like which genotype was used in which study in your database, because that's going to have a huge impact in how we all, as a community, it'll be a huge community service also, just so that we know kind of tracking this thing over time. That was my kind of riff off of the current conversation. My other question was.
Can we address that first? Because
No,
it's an
I need to
important
go soon.
Oh, wow, okay.
I said I need to go soon,
All right,
so I'd like
okay.
to ask my questions.
Well, sure,
Thank
sure.
you.
Okay, well, you won't hear an answer then.
You were mentioning that the VDP, VPD impacted the yields. Did you happen to look at whether it impacted the decline rates?
We did
That
not,
was, I was super curious about that too, because you have these decline rates over time. Like,
do you need an answer or you wanna?
yeah, no, I would love an
Because-
answer. That's why I wanted to ask now before I have to
Yeah,
go.
okay,
Yeah.
so, so the first part of your answer, I think you can maybe address because you did there's some ANOVAs to parse those things out. right? And
Yeah,
I
yeah.
don't think there are like that many genotypes. And again, if Jake was here, he would illustrate that. I don't think that there are as many genotypes there. Yeah, let you take it from here because, it's a lot of it is you analysis we did. So question about the genotype.
And about the meta-analytic, like sensitivity analysis or independence between the studies, I think I'm getting at, is the bigger question I have.
Yeah.
Did you look at the independence between the study,
We-
between your variables?
No,
Like the studies are independent, right? So they're like
Yeah.
papers, so they're independent, right?
Right, each study is independent,
Yes.
but within a study, if you have a lot of measurements
Yeah,
within a study, those can't be just thrown into one big database because they're not independent. And there are like meta-analytic techniques to get at that.
I know them because we published a couple of papers. on
Yeah,
this.
so have
But
you done
this-
that? That
So
was my
the key thing
question.
is that every paper says there's yield decline. So it's not as if the emergent property of these papers is that there is yield decline and in a single paper there were no yield decline. So there are yield declines in all of these papers, even in the non-published.
Sure, it's just whether you're doing your meta-analysis correctly.
So, I mean,
Is the question.
like, there's no single, I'm still not sure about what you're talking about under the hood. So if you can follow up with an email. And we can have a meeting to
Yeah,
discuss
I
those
would be
things.
happy to do that.
So that's the key thing. The other thing that I think very important to emphasize here. So when we look at the data, right, when you look at, you see the data sets and the observations in the quadruple digits, right? So, we can't, there's a trap there to try to project what we want, what we do not want the data to be, but it is clear that there is a decline, right? So, and we have in the proverbial drawer, so to speak, some correlative results on subsets of data that are likely spurious, which we would feel uncomfortable putting at the main result of the study, right? But so that's the trap that we have to be careful about. So we did meta-analysis published last year. For that, we screened 9,000 papers. And we played by the book and we extracted variables and we did some esoteric statistics to really come up with really strong messages. Here, the data set is not that deep, right? So there are things that we have to be very careful about, especially when we come up, and there, by the way, there's no standard, super standard approach for meta-analysis because it depends on the structure of the data set that you have. So we tried
There
random
are some
forest, we
general- I'm
tried,
Actually, in the middle of big one too. There are
That's
some
great.
things, there are best practices.
cool, well, like I said, I mean, we'd be happy to follow up, but I don't think what you're hinting to is completely appropriate with a data set like this. But again, you go to single paper, you have the yield decline, and our conclusions are not countering the single findings of the paper.
Sure.
So that one of the most important quality checks, so to speak, right? So all right, so David.
Yeah, I mean, you know where I'm coming from. I'm a developmental biologist. And I think of everything in terms of developmental biology. And in both grasses, rice, all these things, there are major gene players that control, you know, these transitions, whether or not you're going to be able to leave or shoot these, etc. Those things are under the control typically of just a few genes. I know, and so there are a large number of different genes that, you know, are involved in those processes. I think the perennial businesses is probably a separate issue altogether, it's a different program. But on top of that are the developmental aspects of this plant that have probably been our similar gene networks that are involved in controlling, for instance, tillering and rice and things like that. And so, I mean, that would be the place where I would be looking for variation. You know, the trouble, the difficult with what you're dealing with is you have an obligate outcrosser that's a polyploid for doing genetics, which is so much fun. But there are advantages to that. And one of the advantages of that, and that is that you can pour on a ton of mutagen and not kill the plant because you have all that redundancy. But if you pour on a ton of mutagen, you have a chance of making something like a borer-like dwarf. And so that would be the approach that I would be using.
Thank you for that. Yeah,
Variation.
I think the development question would be relevant, but maybe if after Qiansu's talk, we can address, update, you know, the answer to the question, because it seemed that there is some explanation about why the yields are declining. So,
Yeah, I agree. Let's
Yeah.
transition. There's a comment or question more in the chat, but let's learn some more and then we'll do Q&A.
Okay, thank you all the suggestions and the questions. I give my stage to Qiansu.
Thank you.
Thank you.
Hi, I'm Qiansu. I use the HERF1 and I'm going to talk about the physiological drivers of the intermediate wheatgrass yield decline. And as Walid mentioned earlier, I have 3 hypotheses associated with the interannual yield decline. That is the decline in gas exchange, particularly photosynthetic synthetic rate, and or decline in photosynthetic remobilization to seeds, and or the decline in ability for stress tolerance as the plant gets older. And as you can see here, I use gatherers and carts to move my machines to the fields, and as well as bring the umbrella and chairs to protect me from the exposure to the long time sunshine, just especially during the response curve analyze, and I will talk in detail later. Here is my field that is along the Lampincher Avenue, which started on September 2020. The experimental design is the RCBD with a spinach plot with a 50 kilogram per hog nitrogen treatment, and 6 top-safe intermediate wheatgrass families of the cycle for gradings were used in my measurement. And all the measurements are field-based measurement, and I keep gathering the data, recording the data, including the phenology data. Here's some figures, just example figures here. And I also collected the environmental data from the Simple Climate Observatory. And also use the LICO machines to do the gas exchange dynamics measurement and the gas exchange response curve measurement. The LICO 8 68,000 is a long-destructive process involved in real-time photosynthesis, which measures the uptake of the carbon dioxide absorbed by the leaf and the release of the water in a real time. And here I conduct my measurement from May to July, and the growth of the plant could be divided into 5 stages along these 3 months, including the thinning, the stem elongation, the heating, the flowering, and the seed filming stages. The blue arrow refers to the regular gas exchange measurement. Along the 5 stages, I have 15 times of the regular gas exchange measurement. And I also collected the leaf sample during the thinning, the heating, and seed filling stages for the purple one for the SLA and anatomy data analyze. The orange one indicates the response curves. We have 3 types of response curves, each repeated in the stem elongation, the heating, and seed filling stages. And from the heating stage, each week I collected the leaf sample to just monitor the nitrogen states over times. All the measurements were conducted, repeated in the year 2 plot, except for there's no response curves conducted on the stage, stem elongation stage, because this year has a short window of this stage. And here the table here shows the chamber conditions for doing the high frequency gas exchange measurement. Just I mentioned before, the 15 times measurement during the whole stage. I'm not going to go in detail, just give you a sense of how the environment looks like. And the gas exchange parameters I focus on is the stomatal conductance, the transpiration rate, and the photosynthetic rate. Each measurement day, I have 6 intermediate wheatgrass families to measure, with 3 replications per family and 2 leaves to be measured per replicate. For each measurement, it takes about 5 minutes to get the stable ratings, and in a total, I need 3 hours to conduct the measurement per day. And this time do not include the machine, the time needed for warm up the machine and move the machine to the field. And here, just as I mentioned, one of the response curves is the light response curves. I just trying to get the response of the stomatal conductance, the transpiration rate, and the photosynthesis to the different levels of the power conditions. And here is a figure shows how the light response curves looks like. The y-axis is the different levels of the power conditions, and the y-axis is the photosynthetic rate. And the response curves is able to extract many useful parameters, including this one, the AQY, that is the apparent quantum yield. That this is the slope of the light response curve equals to the photosynthetic efficiency. And this line, the vertical line, refers to the photosynthetic capacity called Amax. That is the maximum rate of the photosynthesis the leaf can have. And the y-intercept of the curve is the daytime dark respiration rate. These 3 are the main parameters I extracted from these gas exchange curves to help me to just explain the first hypothesis, that is there's the yield decline related to the photosynthetic changes. Again, also the VPD response curves and the carbon dioxide response curves is conducted to help me answer the third questions, that is the yield decline. Is the yield decline related to the stress tolerance difference? I use the table here to summarize the chamber conditions for those 3 response curves. And one thing to note, just to say is just there are different levels of the PAR, the VPD, and the carbon dioxide, and each levels last for either 15 minutes or 30 minutes. And here is the time needed for each curves. And I have 3 repeats for each curves. So because this time consuming characteristic of the response curves, I only did those curves on one of the 6 intermediate wheatgrass families. And also the leaf nitrogen measurement was conducted using the combusting method, and the leaf were divided into blade and sheaths to help me more understand how the nitrogen levels change. Also, with the help of Strick's lab, we have the yield and yield component traits, including the green yield, the number of spikes, the number of spikes per meter, and the total pinner number per meter. Also, I'm doing the process of evaluate the individual seed weight, and I hope this could answer the questions from Jerry and other people that if the grain has the fewer or the smaller grain related to the yield decline. And the statistic analysis involved in my analysis, including normalization of the data to degrade. That helped me to have the ability to compare different years data, and also including the a cohort analyze, the correlation analyze, the linear nonlinear regression, and the paired and unpaired t-test. So here the first and the very fundamental question is that is there any decline between the year 1 and year 2 happening on the yield? And yes, the grain yield decreased by 23.4% from year 1 and year 2. And then I want to know what caused this year decline. What yield components drive this decline? First, I look at the spike number, and it seems like there is no significant change across year.
Just ask a basic question so I know what the picture, are these small plots? Are they space plants? What are the plots like?
Can you repeat the question?
Are the plants you're measuring, are they individual space plants or are they in small plots?
I think they are in a very large plant trails and each
Shaping between them.
Rows.
Rows.
yeah, that is a row.
Single solid row.
Yeah.
Oh, single rows.
Yeah, single rows.
Okay.
So
No. I think one's in the plot,
so
so
that's like
4 single rows.
or single rows.
Yeah.
It's a plot, so it's a block,
Okay.
it's a small block that she's operating. in.
I'm just thinking, are the typical competitive dynamics operating that you would see in a field? And it sounds
Yes.
like yes, okay.
But that's an important point for another aspect. It's an important thing.
Okay, so the spike number do not account for the yield decline as well as the thinner numbers. But I found that the seed mass per spike significantly decreased by 12.5% from year 1 to year 2. Again, as I mentioned, I'm during the process of analyzing individual seed weight. And after I got that result, it will help me to answer if there are fewer or smaller grain yields contribute to the decline. And to understand that, can ask gas leaf exchange dynamics explain this decline in seed mass. I first look at the leaf level transpiration rate. I average the 15 times of the seasonal, just the transpiration rate, and found out that the seasonal transpiration rate do not significant change, which suggested that the water use dynamics do not change. But the thing is that I conduct this measurement from the leaf level. This should be confirmed at the whole plant level in the future. And when looking at the leaf photosynthetic sensitive rate, it is obviously that the seasonal photosynthetic rate significantly decreased by 6.1%, which suggested that the decline in carbon dioxide assimilation rate contribute to this decline. And to just trying to figure out is there any other factors contribute to the photosynthetic decline. I just normalize the photosynthetic rate to the stomata conductance. That is the intrinsic water using efficiency. And the yield decline, the decline of this is still by around 50%. This suggested that the decline in the photosynthetic rate is intrinsic, not due to the diffusive limitations through the stomata. And that triggered me to want to know that the decline in photosynthetic rate due to the alternations in the photosynthetic properties, which I can extract from the gas light response curves. And for the AQY, the photosynthetic efficiency, by comparing the heating stage and the state filling stages over the 2 years, there is no year effect of the AQY. However, when comparing the dark respiration rate, I found out that the daytime dark respiration rate increased in year 2 during the state filling stage by around 145%. And by now it's we are able to answer my first questions. That is the decline in the decline of the yield is related to the photosynthetic the gas exchange decline, especially for the photosynthetic rate and the photosynthetic property. And as for my second hypothesis is the urbanization rate dynamics involved in the in contributing the yield decline. I just separate the as I mentioned, I separated the need to the blade and sheaths to help me understand this nitrogen urbanization dynamics, and found out that at different stages the nitrogen level decline consistently, just during the heating stage, the flowering stage, and the state filling stage. And how about the sheath nitrogen level? The sheath nitrogen level is a little bit less when compared to the blade nitrogen content, but it's also decline consistently across the heating, the flowering, and the state filling stages. So here's my concluding part. So the yield decline, the yield of the intermediate wheatgrass declined by 23% in year 2. And this decline was driven by a decrease in the seed mass. And the seed is likely due to a decline of the seasonal photosynthetic rate. But the seasonal photosynthetic rate decline is not due to the stomata limitation or a degradation of the photosynthetic machinery, but is likely in part due to in part of the lower nitrogen accumulation need, causing from the nitrogen-based limitation to the photosynthesis. And this resulting limitation in carbon and nitrogen is likely result in a lower photoassimilate and a lower nitrogen recombinations to the seed. Additionally, the higher respiration during the seed filling stage in the year 2 might also limit the photoassimilate availability to the seed. And as I mentioned, the third hypothesis is that the yield decline is partially is related to the ability, the decline of the ability to the stress tolerance. So here I use the slope, which infers to the sensitivity. To answer the question that is the sensitivity of the stomata conductance to the increasing atmospheric drought increased by stand age when comparing the different ages of the plant during the heating and state filling stage. I found out that the slope of the stomata conductance response to the increasing in VPD increased by over 300% during the heating stage, which is consistent with the hypothesis what Xiaoxing mentioned and his talking. that is the higher VPD might reduce will reduce result a lower yield due to while reducing the stomach conductance and resulting a lower gas exchange. This hypothesis is confirmed by my experiments and things.
What year was your second year?
It's 2022.
2022, that was last.
Yeah.
Year, that was really. The most healthy environment almost in the history of this campus. Right? So
Yeah.
your first year was, yeah, so keep that in mind, right? So last year. I mean, it was. Really, really, really dry, and it wasn't irrigated, right? Your plots were not irrigated. Were they
I don't know
irrigated?
if Jenkins is here, but could answer that, but I don't think they were irrigated. But the previous year was also droughty, and we were really concerned about it.
Yeah,
So both years were really bad
yeah, but that's what I would take a look at though, you know.
in terms of weather. But
Moisture. And
Yeah.
in those 2 years, because last year. Historically, it was probably the most droughty. I've been here 48 years, I mean. It was the driest years I've ever experienced here, or one of the driest,
For being confirmed, no irrigation.
yeah.
But the fact that, yeah,
2 years, right?
So I
The
understand.
2 years were dry.
I'm just putting it on the table, make sure you think that through in terms of. How dry it was these 2 years.
Mark Seeley's data and see how big of an outlier they were. That database from the Minnesota temperatures from all the stations goes back to like 1970. And so you just see how extreme these were relative to normal.
Those 2 years,
Yeah, I mean, because
and the difference between year 1 and year 2.
That's my point.
Yeah.
Right, that's my point, is that if year 1 was extremely well watered. And year 2 was extremely dry, it would be problematic to infer the yield decline only to intrinsic causes. The problem is not the problem, it's actually both years were droughty.
But the second was. Really.
Yeah. We talked about this with Jim, but I think there's a way we can see to what extent this influences, because he was saying that the wheat took a hit because at the same time we're running the primary measuring canopy temperature
Yeah,
on its 500 yield primary trial plots. And we could see that the wheat really was responding similarly both years. So we have yield decline and warmer canopies year 2 relative to year 1. But he was saying anecdotally that he was not seeing that in his intermediate wheatgrass plots, presumably because they have that higher rooting system. But I think ideally we should have soil sensor moistures to use this as a covariate. So that-
All I'm suggesting.
No, that's
really,
not-
really keep
I
that
hope
in mind.
like that's what.
Really keep that in mind.
I mean, it's in our mind.
and a related question from Lee DeHaan is, is it possible that the lower N in leaves is just driven by lower N availability in the soil, or was that constant? Basically, was the trial fertilized
Yes,
each year?
actually, the trial pre-existed so it's a nitrogen treatment trial, actually not. And there are 3 levels, and Prabin or Jacob can, because it's basically, we came in here like to do the measurements. And we focused on the 50N trial, which was applied each year. So that's something, I mean, the change in the nitrogen status of the plant does not seem to be related to the nitrogen application.
Yeah, but that experiment was over, so there was uniform nitrogen during the 2 years.
Yeah,
Yeah,
exactly.
right, yeah.
Sure.
And I think the fact that the other data showed that, over fertilizing doesn't really help, doesn't address yield decline at all, makes me think that it's probably more physiological based, that something about uptake and, deployment of nitrogen throughout the plant is changing physiologically.
Yeah, because that's totally the point, because, I mean, not only the availability of nitrogen has to be there, but something about there's low affinity, high affinity nitrogen transporters in the plant. This is molecular biology could help, by the way, to understand what's happening in terms of, because we clearly see a change in the nitrogen status of the plant. That's unavoidable. We see it. and you dump nitrogen to the plant, it does not respond. So
Where do you think it's going?
I'm riffing here, but my intuition is something about how the plant finds the place with those nitrate transporters potentially.
Well, the biomass goes up, steam doesn't go up. Biomass increases with nitrogen. Steam doesn't. Right?
Up to a
Yeah,
point, right?
Yeah.
Yeah.
So I was just wondering about your variances at the different locations in terms of environment. So I'm wondering, were some environments less variable than others over the course of the 4-year studies? And looking at that data, it looks like year four university is terrible. Does that mean the stand should be replanted after 3 years instead of 4 years? Or do you need more data to make that determination?
This is so, but like just to clarify, part 2, we did not do multi-year.
No, I know, but in that, was, but because I really like the idea of growing degree days, it's also I was wondering, because that would let you normalize across everything.
Yes,
And then you could look at the, and then you could also look over that same window though, like what is the actual variance associated with the environmental factors, and then use the variance in the model as opposed to the actual covariate itself, because you could then see if environmental variability is driving the physiological differences rather than just an environmental threshold.
okay, so I'm gonna re-ask, better word the question. We don't have physiological data for the database,
Oh, okay, yeah.
right? So that's.
Yeah.
Okay, so I get your
Yeah,
point,
yeah,
that we don't have.
No, yeah, I mean, so I guess, is there a way to cheat and extrapolate the physiological data from the second experiment? And I mean, and I confer some of it from those common covariants.
First of all, we don't like cheating. But we try to connect the dots as much as reasonably plausible. And there's a weird thing that happens when you look at the environmental data. I really didn't care if BPD co-trended or not, but it showed up. And it happens to be something I'm interested in. So when we did the actual physiological measurement and we saw a trend like the year number 2, they become more conservative. As soon as the air gets drier, those guys start closing their stomach. So this is one of the ways where we can try to make sense of the meta-analysis like with the.
So I'm just, because it's so cool, and I really like your maps, because you can really see that spatial trend, and then you can really use that then as a decision support idea, if you can get an idea how yield and the spatiotemporal phenomenon are co-varying with something that's easily measured, then you can start saying, well, here's a better environment for this. So it's just really, really cool data, so it's exciting.
You noted that, hopefully we made it clear to the audience here and also elsewhere. Even the data, the VPD, we're not saying correlation, we're saying co-trending.
Right.
The reason why we did different methods, we compared different models for sensitivity analysis with Michelle. And we have various correlations that we don't believe in, like we have, so.
I want to say that I'm glad you're saying that, because the Morris site is part of that patterning, right? And the Morris site is just crap soil. It's just bad yields every single year, no matter what we did. It was just a bad site. So that we can't attribute that too much to the.
That's actually a paragraph in the paper. We have to be careful. The depth of the data set does not give us enough confidence in the biological meaning of the statistical associations. So, and that's actually one of the problems, but. David.
Okay, I mean, to begin with,
Lay it on us, man.
let me challenge you to read up on some reviews on the genetics that control these processes. I think that's something that you guys it will be of value to you to learn what's out there beyond what you're doing now. Having said that, in 2018, I discovered a mutation that reduces glucosinolase in pennycress. I was very happy about that. I grew up the plants and they look like they made 4 seeds that the flowering was delayed. And since this came from an EMS population, I was, being a geneticist, I'm thinking this is a genetics problem. And so for the last years, is that 4 years? 4 years, I've been trying to outcross, select, do this and that to try to fix this problem with the glucosinolates. The glucosinolate line's looking so poorly. I know they can look good because it's the same in canola. Yeah, the glucosinolate related plant looks fine. What I finally discovered was what my issue was a physiological problem. And that is that the plant needed sulfur. I have given the plant sulfur, and the plants are now growing just perfectly normal. And so I'm wondering too, sulfur is also something that that wheat can suffer from. And I don't know what the sulfur content of your seed is. If you look to see if the sulfur content of your seed, does that go down year after year? And so that might be something to take a look at too. And for you guys, just a simple take a look at the sulfur in the seeds after year. And certainly the ground around here, it's just crap for sulfur. Now, the good thing about sulfur is that a lot of it comes from the breakdown of sulfur by microorganisms in the soil during the summer. I don't have that advantage. I have to put sulfate on it. But in your case, when you have something that's perennial and is continually picking up any potential sulfur, that might be one place to look at. In case, I mean, you may already have tried this, but I'm just throwing that out there as something to try.
So just address this. So I don't see the challenge. We love challenges here. What you said, we challenge you to read the literature on the genetics or whatever. Like I wanted you to tell that, because if you have an idea that found something we're missing, I'd love to hear it, because you said I challenge you to read those papers. What are these papers you're referring to?
That you get to look up yourself.
Nice circular argument. Grad students, if you're hearing this, that's an excellent technique.
That's the teacher in me.
I hear you.
One thing that I didn't understand, I thought it was interesting from your part, Qiansu, is so AQY was not affected, but there were lower nitrogen content in the leaves and sheaths. And so you talked about N-related limitation, which in my simplistic understanding of physiology of photosynthesis, it's N kind of equals rubisco, kind of equals the robustness of your photosynthetic machinery. Are there other mechanisms that you could have plenty of rubisco, plenty of chlorophyll, and you'd still have a nitrogen limitation to photosynthesis?
Thank you for your question. So is that, you say that because of the photosynthetic efficiency do not change, there might be other, you mean the nitrogen goes to the rubisco did not affect by this? Is that your
I guess
question?
just, simplistically, this did not change.
Mhm.
Nitrogen content did change.
Yeah.
And so I guess that's a question right there, because the majority of the nitrogen in the leaf and sheath is photosynthetic machinery, right? So what might be behind that discrepancy?
Okay, here, thank you for your question. This here, because I already did, just observed that there is a photosynthesis rate decline. And I want to know what triggers this photosynthetic decline. And when I refers to this one, the normalized one says that the decline is intrinsic. And I want to know what photosynthetic properties just result in this photosynthetic decline, and the photosynthetic efficiency do not change, but the response, the daytime dark respiration changes, and this is the consumption of the nitrogen, this is a photo assimilation. That means that even the efficiency do not change, but the consumption by the plant itself increased. That results the decrease of the photosynthetic the nitrogen content decrease, because the consumption by the first the nitrogen, the photo assimilation produced by the plant decreased, and also the dark response, dark respiration. That means the consumption of the plant of the photosynthetic also just increased. That just this is a circle, just reduced the nitrogen and carbon it produces. Does that make sense?
Makes sense to me in terms of carbon. I don't know, I'm really not an expert on, the details of these processes, but.
I guess his question is, what is the source of discrepancy
Mm.
between, another way to frame it, I guess, because it's between the photosynthesis differences at seasonal level,
Mm.
which mirror well the nitrogen, and why you're seeing, when you do those curves, you don't see changes in photosynthetic efficiency.
Right.
What would be why we are seeing that? What would be speculation, why we're seeing that? Don't worry, it's not
No,
a committee,
no,
but like,
that's
if we
right.
just
Yeah,
bring
that's
some,
what-
this is
that's
how
what
we
this
work.
guy's saying.
This is what we
Yeah.
work.
Yeah.
How we
Good.
make.
Yeah.
So yeah, like this logical leap between the decline was not due to degradation of photosynthetic machinery. But it was due to lower N accumulation. So if there's less N and it's causing N-based limitation. Wouldn't that show up in a lower, wouldn't that effectively be degradation of photosynthetic machinery?
I think not necessarily.
Okay.
You would have, but the time constants would change perhaps in terms of, because here's the thing. I think that one part of the answer, and we're still grappling with this, is that the N measurements and the gas exchange seasonal are made on a large number of plants, so that we have triple digit reps. The curve, I don't know what, if you have experience with doing those light response curves, we do 3 light course, like 150 grand worth of stuff, to just do those kind of measurements. So it's a low number of repetition. Remember, you said it yourself, these are out crossing, so they're not necessarily pure lines, so you can have.
They are not. You're right.
Yeah, so we cannot say with strong confidence that something didn't change with photostatic efficiency, capacity, but it's not as a strong of a signal. And the way we are cautious in terms of giving each step like 30 minutes of acclimation, we will not capture changes in time constant to reach that for those, which is maybe this is what is changing in terms of the photosynthetic response to light.
Sure,
So,
sure,
that's-
sure.
yeah, but that's
Yeah.
a completely fair point.
I mean, the other, if you turn it on its head, you could say, well, the machinery is there. It's not related to N level in the leaf. Maybe in the first year there was luxury N consumption or accumulation in the vacuole wasn't even part of the photosynthetic machinery. But in year 2, you have this stress response, this more greater sensitivity to stress. So you have, when you acclimate it, when you have a nice humid chamber, the AQY is the same, but on a response curve, but under more rapid response or more natural
Yeah.
conditions response to stress, it's not pumping out as much photosynthetic activity, something like that.
Yeah. It's a good point.
Another
Yeah.
guess.
No, it's an informative guess. I think that's something that makes sense.
We have another comment on this from Jeff Berg. Realizing I'm a soil and water guy, I'm thinking the limit of N in the plant is due to soil N mobilization. If drought doesn't matter, how much N is applied if it can't be mobilized? So you're saying the N might be there, Jeff, but not accessible to the plant because there's not enough moisture for it to travel to, for
Yep.
uptake.
I guess that's what I was thinking.
Yeah.
So that year.
So if it can't move, if the N can't move, it can't get to the plant, so, therefore lower N in the plant. Too
Yeah,
simple.
we thought about that, but like if you look at the transpiration rates between both years, and this is like 540 observations, there's no significant
No
difference.
difference. in trends.
No, not at all.
So they have the water they need. It's kind of the.
Or they
Or their
spread it
equivalent.
exactly similar way between both years. This was disappointing, by the way. But the data, again, grad students, the data is the data, right? So, and I think that's how, if there's no significant differences, you deal with it and you move on to the next hypothesis.
Yeah, right, if the transpiration rate is the same, then. And can you make the argument that it's more stress averse in year 2? I'm having trouble keeping track of like
Stomata.
Is this a lot of acclimation that went into this measurement, or was this without acclimation? Because I think that makes a big difference in the interpretation, right?
Yeah, note that the response in stomata conductance, not transpiration rate, which is not the same thing. But the conductance is flux by driving force, so you can have the same transpiration, but you know, you know.
Right, with the bigger driver and the lower conductance, yeah, okay.
But again, good point.
Another comment from Lee, it's possible that carbon input from the roots immobilizes nitrogen in year 2, so. You know, effectively reduces availability. And again, if we're not seeing differences in AQY, theoretically, you know, the leaves have the nitrogen they need to perform photosynthesis at a high rate, or at an equivalent rate between the 2 years. Wow. Well, I want to say thanks to this team for a great set of data and presentations and discussion. I don't envy you. It's fairly complex to parse all this out, so I'm glad that the team is working on it. And are there any other questions before we adjourn?
David wants to know where he can apply some sulfur to a little fly. And he's not joking.
Well, the easy thing to do is just to look at, you have your seeds from year 1, 2, 3, and 4, so see if there's a decrease in sulfur content.
I think we love those ideas, but I mean, I'm not saying no, but the way we approach those types of things, and I think again, it's important to the broader discussion, is that to be parsimonious and you follow the most parsimonious hypothesis, right? So if we can come up with a reasonable hypothesis, because then why not vanadium? Why not whatever, right? Because these things are important for plants anyway at a certain level. So we need to have like a good framework to start with, and we really struggled in the beginning, like where to start, right? And this, like ecology, there's like people trying to think about those trade-offs, and this is being domesticated, so we thought we start from there. We did not invent the wheel. So I think the ideas like these are important, but we would love to incorporate them if they connect in that way.
It took me 4 years to get there.
I have a crazy idea.
Yeah.
Greenhouse study.
Isn't part of that story though, that the domesticator, the selection was selecting against a thing that was a sulfur containing compound, like would there be a reason thing that that's what's going on in wheatgrass?
So that was the whole, well, I'm talking, so the wheatgrass, I'm just saying that wheat also has.
Oh, okay, yeah, all right.
That's the connection I'm making, not that it has to do with grass.
Okay.
But the amino acid content of wheat is a reason.
Sorry, yeah, I forgot that part of it.
Either that or start burning more coal.
Can I make a call? Can I make a call to the community if people are around? This is something we're struggling with in our experiment. So we need two things, ideally. We need to work on pure lines because of the outcrossing problem and the variability of the responses between half brothers, half sisters, and that push us to have replications in the triple digits over the season. Right. That's for us is something, if those lines are like, if year 1, year 2 lines are available and they're like pure lines, but we can work on them on the same experiment, that would be great. The second thing is that if someone has access to a unicorn, even low yielding, but does not show a yield decline between year 1 and year 2, we would be really interested. So these 2 requests, because those things exist.
Well, there is a data set from Rosa that comes out of Don Bellixson, where the yields have been more stable than any other place, any other environment that I've seen. I don't know whether you've talked to Don or not, but
We're busy with those types of
no, I understand, but in terms, I think there was some information passed around, maybe they didn't get to, but I'll make sure you see that data set. Right?
And that's with the burning, residue management through burning, which may or may not explain why.
And
Look at that.
and elevated levels of nitrogen. And the other one is, the folks in Lee, right? Lee has told me that their decline isn't as great as we have here, but their yields are lower, I think, in most years because of the dry conditions, right? Lee, you still there?
Yeah, I'm here.
Tell us about your yield decline. I think we asked you last year. Remind us. Does your
Our yields fluctuate a whole lot more based on rainfall year to year than it is on a systemic long-term decline. So if we have a dry year, it's going to be low, and then you have a nice wet year, it's going to come up. It fluctuates a lot with the rainfall.
But what's the fluctuation in your old stands?
You can have an old stand with as long as it's not too thick. So for us, thinning has kept the yields high in general. And it seems like in y'all's fields that doesn't seem to work as well that way. But if I have a breeding nursery that's kept at a low density, the yield can stay pretty constant for 5 years.
That's using severe rototilling.
Yeah, yep, keeping it thin. As long as we don't get into a severe drought like we have right now.
Yeah.
But once you hit a drought year, then the yields are going to plummet. But then if it rains next year, it's back up. And sometimes a drought year seems to cause a better year. If there was some decline happening, that drought year can help rejuvenate the stand, the next year.
We'll make sure that we share some of our kerns of seed so you guys don't starve this year.
Yeah, that question about heavy grazing, we had at least a few farmers that have done that. And, it's not a good experiment, but we got pictures of both sides of the fence. And definitely the side with no grazing had no heads, and the side that had grazing produced heads that next summer after the heavy, hard grazing all winter. So, yeah, I think there's various kinds of stresses can help. So, I mean, it's a weird thing because y'all are talking about like the plant in the second year becoming more sensitive to stress. And I see that too. I can agree with that as a physiological change. On the early first year, it seems to make seed no matter kind of what the situation is. And in the second years, it becomes more susceptible to stress. It becomes kind of hypochondriac. Any little stress, it doesn't want to make seed after that, being like a physiological regulatory change. On the other hand, severe stress that really thins out the stand seems to kind of reset a little bit. If you come in with a disking or burning, some severe disturbance, you can kind of make it think it's young again.
It's funny you saying that, Lee, because in Tunisia, where I'm from, we burn the old date palm trees because these are only single stems, right? This is why we call them phoenix dactylifera, because if they go long in production, they remove the leaves and they burn the stem, but not to kill the plant, and then picks up productivity again. And so,
well, those of I don't know whether Nancy's online, this phenomena that we're looking at here is old business to Nancy and I, and those of us that work in the grass seed world, right? This is exactly what the hell we see, right? You go in, you plant Kentucky bluegrass and these other grasses in northern Minnesota. This is the same damn trend. And then we come back, either take them out or renovate them, right, to maintain, but the yields through the renovation process have never come back to that first and second year yield. So this is same phenomena. Those of us that work in the grass seed world fight year after year after year, whether it's in the Pacific Northwest or here in Minnesota.
That suggests that there's something sort of deep genetically going on, right? About what's actually controlling stuff, like the signal or whatever it is.
Well, those that work in the forage and turf seed business call it becoming sod bound, right? Basically the intensity of the shoots and thinking of that as competition,
But if it were just that, then thinning would work better than it does in Minnesota, so it does seem like there's
But
multiple
there's
factors.
a certain point where it's like, okay, it becomes sod down, but why does the plant respond to that? Why does it say, all right, now this is my sod down response instead of my sod down response being make more seed, like keep making more seed? Right, that's like something.
Is it just a purely competitive thing where
Yeah.
tillers are fighting each other too much, so none of them can succeed, or is it, you know?
But we also have that Phoenix thing, we burned the Kentucky bluegrass in northern Minnesota.
But beyond the Phoenix thing, that she spent 2 years really doing very intense experiments, and there's some evidence to indicate that something changes in the plant itself. You know, physiologically, in terms of photosynthesis and nitrogen, that I think these are two important findings.
Yes, absolutely.
That kind of gear point things to a certain direction. And there's a lot more to figure out for sure.
I have an anecdote to throw in here on nitrogen. My brother in Northwest Iowa has some old intermediate wheatgrass fields. And he put on 200 pounds, 100 pounds and zero in the prime corn ground there. And it was totally sod bound, but it was a dry year, but nonetheless, the 200 pounds of nitrogen did not increase the biomass yield, and the 100 pounds didn't increase the biomass yield. And yet he sampled nitrates the whole time, and it stayed below 2 parts per million. And it didn't appear above ground. So somewhere nitrogen vanishes near this plant.
It just captured the roots and burned off as nitrous oxide. Just gets rid of it.
Hopefully not as nitrous oxide.
Sounds like.
Okay, we're getting in a wrong direction, we're burning and we're using, you know.
It's a climate solution, everybody.
Maybe we should close up shop.
Maybe those roots just squirrel it away, hold on to it.
Yeah, that's what a soil scientist suggested, was that even 200 pounds of nitrogen, if you're building soil organic matter, is a drop in the bucket. So 200 pounds of nitrogen going into soil organic matter vanishes instantly. So
yeah,
it's hard to keep enough nitrogen in the soil once you have perennial roots there.
sure. Alrighty, thanks everyone. See you next
guys.
week for next week is the last meeting. Can't even say of the semester's over, but we have so much demand. We have one more meeting next week and then we're done for the summer.
We've got Qiansu.
Thanks, everybody.
Thank you.
Thank
Who is
you.
it?